It's recording. This is them walking away. I forgot I set the clock so that it actually told the correct time at some point. It's a little bit behind again, but. Oh, well.
Hope the graph is what you wanted, it's in color, so.
Say it again?
The graph,
Oh. All right, we're all here. That's easy. One second, right there. Yeah. You know, eating every one for a week and then taking a week off, doesn't do much for my memory of names, so I apologize for, I'll still be referring to a cheat sheet here. Except for Ronald, I remembered Ronald.
yeah, cause I saw you the other day.
So start out with, any questions?
I have a couple. One for the lab graph. Do you want us to do that on Excel, or does it matter what spreadsheet we use?
I wanted, no, it does not matter which spreadsheet program.
Okay.
Just make sure that, you've got the equation, the R squared value, the trend line, the data points, graphs, proper place, units.
And the next question is, on the master set, it asks for the yield strength. What is that? Is that like,
The yield strength is the point at which it falls officially into plastic deformation.
okay,
There's the elastic limit where it actually will not go back to fully back to its original shape. Yield strength technically is when you hit a strain of 0.002.
so the plastic deformation is the yield strength? When,
Yeah, I think in this one I was putting about the same one. Let me look at the wording again.
because they are really,
You're done here?
all right,
Okay, so cylinder, machine, stretch of material, okay, yada, yada, yada.
the moment the cylinder enters plastic deformation, that'll be yield strength.
What is the strain? Wait, sorry, which one are you on?
Well, I'm on this one, yield strength, number 12.
So we assume that the stress of proportionality limit is about the same as the elastic limit in the official start of plastic deformation. Ooh, I need to reword that. Young's modulus, what I'm looking for is just the stress value when the strain is, I guess you have a strain value there. And you have the Young's modulus, don't you?
Yeah, Young's modulus is right here.
Okay.
This is the answer to
Yeah, so stress divided by strain is Young's modulus. You have strain, you have Young's modulus to solve for stress.
So this is just the stress.
Yeah,
Okay.
yeah, yield strength is the stress. Yep, sorry about that.
Because, then it'd just be the same as when it enters plastic deformation. Because this is the stress whenever it enters plastic deformation, and this is where I got this number. I use this number
To get that.
just divided by.
That's quite possible, like, yeah.
I have a work right here on a different page.
No, it's a matter of, I wanna read the question again. Alright, so it gives you the initial dimensions. Then just calculation stuff. Moment cylinder, there's plastic, let's see. You pull on it with that amount and it tells how much it stretches. It officially enters plastic deformation, but consider what is the stress. strain. I got two interpretations, I'm trying to remember what I was thinking. Since this is the first, it's a version 1, yeah, we'll just say it's the same as the other value, assuming it's, the other value's right.
Hmm.
And then at some point while I'm reading it, I might go, oh, okay, that's what I was thinking. And then for version 2, I'll change it. All right, other questions? All right. We last left off where we had a mass dangling from a spring, and we figured out what the theoretical period would be, and we figured out and then we found the experimental period, and they did not match. I think that's where we left off. So we got a believe so kind of nod, and then a
Where in the
blank
book
stare.
was that? Cause I didn't have my book last time we was here.
So the last time, we had found that for something in simple harmonic motion, or something that obeys Hooke's law, which also follows. So if it obeys Hooke's law, Hooke's law, then
That's why I'm getting, like, every subject, yeah, cause it ain't full.
let's see if I can actually write English words, then the object will oscillate in simple harmonic motion, which is chapter 14. And so we found that if it's obeying Hooke's law, Hooke's law tells me that the force being applied to the object from the spring is negative times the spring constant times the position of the object. And that, I think we got this far, that the angular frequency is the square root of K over M. Yeah, be nice for confirmation, that this is something brand new.
Yeah, it was, yeah, that's right.
So we got that far?
Yeah, we got it.
Okay. And then from that, we ended up with omega is equal to 2 pi times the frequency, or, no, that's right, we went straight through the period is equal to 2 pi over omega. And so we had a spring, well, we're gonna have to sort of redo some of that unless the slinky is still here with the rubber bands on it. Let me see if I happen to take it into my office. All right, so let's redo it. Now, my recollection is that we did not get to the point where you actually told me why that there was a discrepancy between,
You had just told us why there was a discrepancy,
and why was there a discrepancy?
because of the weight of the spring, or slinking.
Gonna nitpick that on the weight.
The mass.
Man.
Yes, there we go, all right. So we got that far, all right, so now let's run the experiment again. We'll come up with a new value for Hooke's law, or a new value for the spring constant. We'll take the mass into account of the spring and see how close that we get. So I need a stand. There we go. There we go. Get this about the same height. That's really good enough. And slinky. And rubber band. Alright, so if it falls off, I should be able to reproduce that. Put it out a little bit farther because I don't want it hitting the table. So to find Hooke's law, just as you have done in the lab, we need to figure out how far does it stretch as I apply a certain mass to it. I don't need to take the mass of the slinky into account at this point. And masses. Oh, I need to figure out where that is.
The length.
So we'll just measure distance or position from the bottom. So assume 0 is the ground. And so it's like 97.2. So the initial position. So imps of 8 for hanging mass in kilograms, and then position in meters. So 0.972 meters. Now sometimes in a lab, I will ask you to put it in whatever you're directly measuring in, so centimeters and grams. However, if ultimately we're gonna be heading into SI units, it's nice to start out there too. So now I apply a mass. So we're gonna have two positions here. We have the lower position and upper position. I basically want the middle. So the bottom one is 85.7, and the top $89. Stop. $89.3. I'm hoping somebody wrote those down.
Should track that as 0.4.
So what were the two numbers again?
175 even, or 175, so then about 85.7, 89.3.
85.7, 89.3. That is horribly good. 89.3, and so we end up with 0.875. Okay. That was 0 on it, and the mass I put onto it, and I'm just gonna trust them for right now. That is 20 grams, or 0.020 kilograms. Now, in theory, we could find the Hooke's law from that, assuming that it maintains a linear relationship, and, the brief look at people having done the mass on a spring, it is generally linear up to a certain point. But let's go ahead and add a 50. We'll get a third data point in there, see how close we get. I'm gonna take the 20 off and so we'll just have the 50 on it. So 0.050. Now, if I were doing this properly, I would get algebraic balance and not trust the manufacturer. And experience tells me it is somewhere around 50 grams, but it's not gonna be exactly, probably off by about 0.1 grams. Because, well, the difference between something that's really close to 50 grams and what we get is the quality control. So sometimes you get lucky and it's really close to it, and sometimes it's, I think they promise you're within 10%.
Is the Hooke also measured?
The Hooke should be part of the mass that's listed there. I would hope so. All right, so the bottom is, it's like 69.9, and the top 74.2.
That's 72.05.
So what did you get?
72.05.
And then put it in terms of meters, 0.7205. And I'm actually on screen, okay. So let's see what we get. So when trying to figure out Hooke's law, what we really are concerned about is not the exact position, because I could have set 0 to be there instead of the floor and gotten different positions. What matters is the change in position or the displacement. So if I did mass in kilograms, hanging mass in kilograms versus position, versus displacement. Well, when nothing's hanging on it, it's not, the displacement 0, that's its starting point. And then when the mass was 0.020, well, the change there is the displacement. Like 0.8.
0.8, 0.097.
0.097. Now, whether that's positive or negative displacement depends on how you've defined it. In terms of finding Hooke's law, the value for k should be a positive number. And the negative sign is taken into account there. So, if you have negative displacements, it's not technically wrong, just not necessary, okay, for what we're trying to get here. And then 0.050.
0.154.
For this one?
Did I get that one?
Yeah.
Not 154?
It's 0.7205 minus 9.
Yeah.
0.72, right? It's 2.2515.
2515, okay. So that makes me feel better, because the other one I was thinking, wow,
Oh, yeah.
something's way
So
off.
you're doing the original number?
Yeah,
Okay.
displacement's always from wherever the initial 0 is. Okay, I see what you did. All right, so in an ideal world, I could just do this divided by the weight of that, and this divided by the weight of that, and I'd get the exact same value. Are we going to? Probably not. Do recognize though that it is going to be, if I got the spring hanging like this, and I got the mass on the end of it. I have two forces acting on the mass here. I have its weight acting down, and I have the force from the spring acting up. Yeah, mass is what I use. And so, what's the formula for weight?
Mass times acceleration.
All right. And the force from the spring. Formula?
K over N, right? No, K over X.
Not K over X.
No, distance.
K times displacement index.
K delta X. Now, I'm not writing the minus sign there because the negative sign is just telling me the direction, and I already indicated the direction with an arrow here. And so if this is an equilibrium, so it's sitting there not accelerating, then these two should be equal, so K delta X should be equal to mg. And so K should be mg over delta X. So in our first case there, if we just did the one sampling, we'd have 0.02. What is the value for G?
9.8.
All right. And then what's the sampling? What's the value for G?
9.79.